So I'm going to cover the last topic in the first week of interpolation, root finding derivatives, the first week of numerical methods. We're going to go over another root finding method, and I mentioned it before. And so if you remember, root finding is you're trying to find the zero of a function. And so you're trying to find, you have some sort of analytical function in this case, and you're trying to find, all right, where is that going to end up equal to 0? And so the Newton method, or the Newton-Raphson method, is a way to do that using the function and its derivative. And it actually ends up being a simpler method than the bisection method, which I showed you before. And what's more, it actually is faster. And so why would we end up using the bisection method over the Newton-Raphson method? Well, one reason is because, well, this requires one input and its derivative, and in order to have the derivative, it needs to be analytical. And so the bisection method actually can work without the function, quote unquote, being analytical. You could use interpolation with numeric data and kind of get pretty close to the final answer. And so using combination of interpolation, which I covered obviously, and the bisection method, you could actually use the bisection method to find the root of just about any function, any set of data. You could find a 0 of it. The Newton-Raphson method, I mean, I think there are some numerical approximations of it, but primarily you need to use the format I'm going to show you right now, you need to have the function and its derivative both. And so that becomes a problem. Like, let's say what if you can't take the derivative of a function? I think you can of most functions. What if you don't have the solution available very easily, right? That's one problem. Other problems can be you have to have a good starting point. So if you're at a point where it might diverge, where the slope actually doesn't point to the 0, because that's kind of the whole point, is you see that you have this slope here, and it's kind of, you're assuming that the opposite direction of the slope always points at the local maximum or local minimum. And that's true for the most part, but there are cases where that could not be true, and so it might diverge, which means it goes to infinity or negative infinity, and so it can't be used. And then there can be derivative issues where, like, the derivative's undefined or very close to undefined, and so then you might end up having a divergence there. But overall, you can use it. And so here's the quick and dirty derivation here. You basically have the definition of f of the derivative and the slope here. And then you kind of back it out, and you end up with this solution on the very bottom. I don't care about the derivation for you all. It's here in case you're interested in those things. But effectively, what you have is your next point. So you have your first guess, and your next guess is going to be equal to your first guess minus the function evaluated at that point divided by the derivative. And it's just that simple. As you would plug this into MATLAB or do it by hand, and you'd end up getting to your answer in just a few iterations. So you're basically keeping on guessing until you get to a point where your function is equal to 0 at that point, effectively. And so you want to start with a point near 0, and that near is relative. It can be far away from it as long as you're not closer to another 0, basically. But you want to have your starting guess be fairly close. And so here are the steps. So I'm going to give you a summary, kind of an algorithm to use, like I did with the bisection method. And this one's actually much simpler. And so you choose an input near 0, and then you basically start the loop, more or less. But you evaluate both f of x and f prime of x, and then you start in the loop, and you calculate this right here. You calculate xn plus 1 is equal to xn minus fxn over f prime xn. And then you want to check if your new f of xn, n plus 1, so you want to check now if your function evaluated at that new point, xn plus 1, is close to 0. If it is, then you leave. If it's not close enough yet, you keep iterating steps 2 and 3, basically, back and forth, back and forth, back and forth, until, like in the bisection method, you get an answer that's close to 0. So how does this work? And so what I would like you to do, if you're willing, obviously I can't make you do anything, but go through this process by hand. I'm going to walk through what it would look like, the tabular data, basically. And so you start off with a guess of 0. And your guess is for this function f of x cosine x minus 2x. So this is kind of how you would do it by hand. You'd make a table of exactly like this. You would say, all right, my starting x is 0. My function defined there is 1. You plug 0 into this, and you get 1. F prime is going to be equal to negative sine minus 2. And so your answer at x equals 0 is then negative 2. And then you plug it into this equation. X of n plus 1 is equal to 0 minus f over f prime, or x 0 minus 1 over negative 2, or 0.5. Then you plug 0.5 in, and then your next step would be this second line, and you'd keep calculating this, plugging it into this equation every time, and eventually you'll get, all right, my answer is now 0.000 f of 0.0000088. And so that's really, really close to 0, and so you're pretty close to the final answer. And so I've gotten it down to, actually it's more than 3 significant digits, but I've gotten it close to, I've gotten it down so that I have x of n within 3 sig figs, right? So it's the difference of between steps 3 and 4. It's the difference of 0.4506 to 0.4502. So you're basically the same, right? Your answer is 0.4502. And so basically what I'm kind of getting the point at is with the bisection method, this would have taken many more iterations, and you need 2 guesses to start with. And with the same process, in 3 iterations, one after the first, 1, 2, 3, you've effectively converged onto a pretty good answer. And what's more, you've done it with only 1 guess and with 1 very straightforward equation. Really, you only have 2 steps in here, right? Whereas before, I think there were like effectively 7 or 8 steps with the bisection method. And so it's a lot more straightforward. And so my goal is going to be now, I want to do the same thing, and instead of 3-digit, I want it to be 7-digit accuracy. So I want to find the 0 for the same function. I know the answer is going to be 0.4502, and I want to find the 0 to within 7-digit accuracy with a starting guess of 0. This basically solving the same problem that I just showed you, and I'm just going to show you how would you create a MATLAB program that does these same steps. And so hopefully, if you've gone through the steps like I was asking you to do by hand, go through and do everything following these 4 steps, what I'm going to explain to you should be more straightforward. Realistically, honestly, it's pretty straightforward in general. And so I'm going to define my function the same way I did before. I'm going to do fun is equal to, and define an anonymous function fun, which is going to be this function f of x. So cosine x minus 2 times x. There's my function. The reason I'm doing it this way, like I've told you before, so now I'm making a general Newton-Raphson solver. And the reason it's general is because I have this function here that I can change and solve the 0 about any function. And so I'm going to say x is going to be equal to 0. So my initial x is equal to 0. My f of x is equal to fun of x, right? And now I'm gonna define fun prime is going to be the derivative of this function. And so if you don't know derivatives, this will get a little bit trickier. But the derivative of cosine is negative sine. The derivative of 2x is just 2. And so there's my function prime. So if I do f prime of x is going to be equal to fun p of x. So effectively all I need to do to change this Newton-Raphson solver is I need to give as an input the function and the derivative of the function. All right, so I now have my initial guess, and maybe I should say so, initial guess, and then I'll comment here, define function and derivative right there. Sure. I have my initial guess here. So that was step 1. Choose an input near 0. And then step 2 is evaluating both the function and its derivative. I've done that. So these are steps 1, 2, and 1 and 2. And so I'm commenting this just for your own clarity as I'm going through it. I'm explaining it, but hopefully, if you were to go back and just like screenshot what I have at the end, everything will make sense. I made my initial guess. And now I need a while loop. So this is going to be the same as the bisection method. I'm going to execute this as long as my my f of x is less than or is not equal to 0, basically, right? And so this is while fx is the absolute value of fx. That was important last time, remember, because fx could be positive or negative, but you're really wanting to see how close does it get to 0. So I want to see while absolute value of fx is greater than, and then I gave you a 7-digit accuracy, so I want to do 1e minus 7. And so this is your error, right? So I'm trying to continue to go through this algorithm, calculate step 3, and evaluate the function, calculate step 3, evaluate the function, until my fx becomes less than my error tolerance, right? And so my error tolerance that I gave you was 7 digits, so this is going to be my 7-digit accuracy right here. And so now, like I said, you just kind of, you go through this equation. So x new is going to be equal to x minus fx divided by f prime of x, right? And so now I've calculated this, and now my new, so what I could have done is I could have done x, but then I'm going to do x. I'm going to evaluate f. Now I have to evaluate both f and f prime, because my entire goal is going to be to compare fx to this number at the top of the while loop. So I've calculated my next input, and now I'm going to evaluate fx and f prime x the same way I did here, right? So fx is going to be the function evaluated at f new, so x new, and then my f prime of x is going to be my derivative function, which I've defined up here, remember, evaluated at x new. There. And now in order to bring my, oh, I think I might have done something, but in order to bring my x new over to the next iteration, if you look, I defined my equation in terms of x, and so now at the end of this loop, I'm going to need to define x is equal to x new. And so what I could have done is I could have just defined x up here and skipped this step, but that's fine. So I wanted to do x new is going to be xn plus 1. Right here, I evaluate f of x and f prime of x at that new point, and then so that I can compare using this statement, so that if f of x gets small enough, close to 0, I want to leave the loop and say I'm done. And then at the end of my loop, I say, all right, my x is going to be equal to x new because I used x in line 12 here. So I have to update that every time with my new x value. Okay, and so let's run it. Oh, and then let's also check the iterations. So I'm going to do iteration is equal to 0. I'm starting out with it equal to 0, and then I'm going to update it every time. This is going to be like my counting variable. If you remember, and whenever I've done while loops or for loops, I usually have some sort of counting variable. And so I'm going to do that just so that I can count how many times I go through this loop before I get the final answer, before I leave the while loop, and I've determined that my f of x is close enough to 0, and so now I have my x value, which will be my final answer. Okay, let's see what x is. 0.4502, same answer I got before. And it took 3 iterations to get 1 times 10 to the 7th accuracy, which realistically is true, because if you looked in my previous example, 3-digit accuracy was only 2 iterations. My 7-digit accuracy was the 4th iteration here, right? So I did the initial guess, second guess, third guess, then 4th guess. I got to 7-digit accuracy, which is kind of the same answer I got here. Let's say I wanted to get it to 10 to the minus 9th. It only took 1 more iteration, and I basically got the same answer, right? So, because it's not even going to display anything more precise than 4 digits. So I've solved the problem, and that's all you need to know for the Noon-Raphson. It should hopefully have been pretty straightforward for you all. And so if not, what I want you to do is now If it is or it isn't, I want you to do this problem 5. Go through the evaluation. I have the answer to my previous code here, right? And so if you really need to lean on it, you can. This is another way I went and solved it, and I did some proofs and stuff too. Did some more thorough analysis. So you can use that as a starting point if you really need to. But what I'd like you to do is I'd like you to start from scratch for problem 5 and find the 0 of this function, which we've looked at a little bit before. And I want you to find the 0 for this function, starting with a guess of 0. Oh, I don't think if you can do a guess of 0. But what I want you to do is go through problem 5 and start to try to work it out for yourself. And so what I want you to do is write a MATLAB code that goes through each of these 4 steps and continues to iterate until you get to the final answer. And as normal, once all of these have been submitted, I will post the final solutions.